Right, so here's where we were last time. We talked about several things in this section on cross products and determinants. We talked about right-hand order. Right, this picture we have here is an indicator, sort of a visual aid as to how you decide on right-hand order. So specifically, if you have vectors ordered A first, B second, C third, index finger parallel to the palm in the direction of the first vector, middle finger, orient your hand in such a way that you can bend your middle finger in the way that middle fingers would like to bend toward the direction of the second vector. Your thumb will then point in the direction of one of the sides of that plane, defined by A and B. If C is in that plane, or excuse me, on that side of the plane, the listing, that order of the vectors is a right-hand order. And we talked about determinants. Here's our formulas for how to define determinants. And there are some interesting facts about determinants. Specifically, there's this very strong relationship between order and determinant and area when you're talking about a pair of two vectors. Then likewise, very strong relationship between order, determinant, and volume if you're talking about three vectors in R3. Okay. Then I wrote down the definition of the cross product, wrote down a couple of preliminary algebraic properties that are nevertheless a little bit weird looking. They're interesting. They're strong enough to be interesting, but counterintuitive enough to be concerning. Right? So heads up when you're doing algebra of cross products. They don't behave in sort of the intuitive ways that you would sort of expect based on all the algebra of all that you've seen since elementary school, middle school. So the algebra of cross products is weird. And we wrote down a few other properties. We made this observation about orthogonality, and we made some algebraic observations about how you can write down the cross product as a symbolic determinant, and correspondingly how you can write down the triple product as an actual determinant. And this is a really powerful fact here, and maybe again I'll circle the one below it here, a little bit prettier to look at. Three vectors, the triple product and the determinant, same thing. Okay, and this is our foot in the door to prove some really interesting facts about cross product, because again we know cool facts about the determinant, we know cool facts about the dot product, and so from this we can infer cool facts about the cross product. So here we go. Okay, first thing I want to do is I want to revisit this old theorem that we talked about last time. You have two vectors, then the cross product is always orthogonal to both of the original vectors. And the way we address this, now last time I made the observation that it's addressed by computing these two dot products, and then I said plug and chug. Right? We have a formula for we have a formula for the cross product, we have a formula for the dot product. Write it down, put together all the terms, and multiply them out and see what cancels, and it turns out everything cancels, and sure enough you get 0. But here's a way to see that geometrically now. Okay, using this triple product observation that we have here, and therefore kind of without doing any algebra at all, which is nice. It appeals to the laziness in us. So here's the idea. Keeping in mind we're interested in the dot product of V with the cross product because we want to show that the cross product is perpendicular to V. So check the dot product is 0. Well, now that we have the previously done algebra, we realize that this is a triple product and therefore a determinant, and therefore, based on what we talked about last time, a volume. So the dot product we're trying to compute by way of a connection to this, to that, is a volume of a particular parallelepiped. Now specifically, it's the volume of the parallelepiped who has two vectors defining it that are actually the same vector, and then the third vector defining it is that other vector. Now if you have parallelepiped defined by, well, it's really two vectors instead of three vectors, the point is its volume is 0. right? You look at the little box, box that's defined by these three vectors. Well, it's a flat box, ready for recycling, right? It's been pushed down, smashed down. So what's the volume of that box? 0. So if the volume is 0, that means the determinant is 0. That means the triple product is 0. That means that this dot product is 0. And that means that this vector v and this vector v cross w are perpendicular. So no algebra, right? Purely geometric argument making connections that we've previously observed. So I think it's a lovely little argument. It's also a nice exercise, nice little mental exercise in making use of facts that we already know, and as such is good practice for you guys in making sure that you're sort of comfortable dealing with these different ideas. Is everybody on board with what just happened? Here's another one. Cool thing that we can do. This result here. If you have a pair of vectors in R3. Now, that's sort of unexpected. We've talked about geometric results if you have 2 vectors in R2, 3 vectors in R3. Here we have 2 vectors in R3. Now, they define a parallelogram. And so how would I compute the area of that parallelogram? Well, it turns out, a little bit counterintuitive, unexpected anyway, but the area of that parallelogram is the magnitude of the cross product of those 2 vectors. I'm going to prove this result for you, again using facts that we've already seen. By the way, here's that notation again we talked about previously. That's my little shorthand notation for a parallelogram defined by the 2 vectors v and w. Right, so it's another mathematical bank shot. I'm going to start off by computing something we're not actually really particularly interested in. Namely, I'm going to compute this determinant. It's a determinant of a matrix whose rows are 3 particular vectors. The 3 vectors are cross product, v and w. Now, I can compute this if I want. Why I want to compute this is not at all clear, but let's do it anyway and see what happens. So, in fact, I'm going to compute this thing twice in 2 different ways. And then I'm going to observe that the 2 things I compute are equal. So, here's the first computation of it. This, as a determinant, is a triple product. So, as a triple product, it's the first vector dot second vector cross third vector. So triple product. Right, does everybody see the triple product? Now, coincidentally, this triple product, weirdly, it ends up being a dot product of a vector with itself, which is magnitude squared. Okay, now, so what? It's not really what I was interested in. Nevertheless, this is sort of step 1. This thing that I'm not interested in is equal to that. Okay. Now, let's look at this thing I'm not interested in again. And a different point of view I could take on this determinant is that, well, it represents a volume. Right? This represents the volume of a particular parallelogram, at least its absolute value does. Okay. So it's the volume of the parallelogram that I get by parallelepiped, excuse me, that I get by looking at the 3 vectors. By the way, question, I kind of swept that under the rug previously, but in fact I know that this is actually equal to the volume. I don't even have to say absolute value. Why don't I have to say absolute value here? Why, in other words, how do I know that that's positive? Maybe it's not positive, perhaps. Couldn't it be that that's not positive? In which case I would have to say the absolute value of that determinant, but I claim I don't have to. This is kind of a delicate little point here. Yeah?
Yeah, you saw in the last one that it's something squared.
Yep. That's exactly right. Look at that. It is a square of something, therefore not negative. So, yeah, cool little observation. Okay, very good. Right, so this is equal to that volume. Now, how would I go about computing this volume? Well, good news. I have already shown that this vector is perpendicular to both of these vectors. And let me do those in a different color. Both of these vectors. And being as it is perpendicular to both of those vectors, it's therefore also perpendicular to this entire parallelogram. So what I'm interested in computing the volume of here is a certain two-dimensional shape that has an area that I can talk about, and then times a height. Right? I can just view this as being the height. So I've got a base times height kind of situation. And volume is just area of the base times the height. So let's write that down. And here it is. The area of the base, what I have in blue, times the height, which is the length of that cross product. Let's see if I can get this both on the page. No, not quite. I'll zoom out a notch. There we go. So this volume is the area of the base times the height, which is the magnitude of that cross product vector. Okay, so I've now, again, computed this same thing two different ways. I computed that volume, that determinant. On the one hand, it's equal to this. On the other hand, it's equal to that, and therefore these two things are equal to each other, as we see here. And now let me zoom back in for ease of seeing what's going on here. So we have this equation, and I'm just going to cancel one factor of magnitude of V cross W, and I get the desired result, namely that the length of the cross product is equal to the area. So, there you go, a little mathematical bank shot. Again, we were not interested in this determinant, really, but it was the computation of this determinant that gave us sort of a foot in the door to get area and length of the cross product both on the page at the same time. It's a very clever little argument. This, by the way, is an example of a proof where all of the steps individually are steps that you can make sense out of, that you can understand here as a Math 212 student, but I do want to point out that this is sufficiently clever that you might not have thought of this proof yourself, right? In other words, how would one have known to start by computing this determinant? Well, you probably wouldn't have thought of that, right? So that is a really insightful step, and having the insight to make that first step, not something that, you know, in your first time through the material you would think of. But all the rest of the details I do expect you to follow and understand. Now, even though I wouldn't expect you to have thought of that on your own, that first step, now that you've seen it, I do expect you to know that. Right? So if I ask you on an exam to prove this result, to prove that the area of the parallelogram is the magnitude of the cross product, yeah, I expect you to be able to do this whole proof. It's just don't feel bad if you're thinking, man, I never would have thought of that first step. Don't feel bad about that. Okay, so moving along. This next corollary is just really a restatement in a different way of what we just talked about, namely the magnitude of the cross product is equal to the area, which, by the way, is equal to this little bit of trig here. And that's just an observation. If you look at this picture, the area of this parallelogram, here, let's see, I guess I'll do this in green. The area of that parallelogram is the length of V times that height, which is length of W times sine theta. So just a little quick trig observation there. Is everybody comfortable with the trig in this? Make sure to refresh yourself on your trig. That purple line there representing the height is that hypotenuse times the sine of that angle, thus giving this, and allowing us to slight rewrite of that theorem that we just proved. Okay. All right, so at this point we do have a pretty interesting point of view on our cross product, namely given a vector v and a vector w, I know that the cross product is on that line perpendicular to v and w. I know which, in some sense, I know which direction that the length, that the cross product points. It points along that perpendicular line. There's only one such line. That's the direction v cross w points. I also know by the area of that parallelogram, I know how long the vector v cross w is. The length of the vector is equal to that area. So that tells me that distance. It's almost like I have a completely geometric characterization of the cross product. It's tempting to say the cross product is the vector perpendicular to v and w whose length is equal to that area. Right? So I've described the cross product in terms of perpendicularity and area, very geometric ideas. There's just one little shortcoming, and that is there are actually two vectors that are parallel to that line and have that corresponding length. Namely, there's that one and there's this one. So the question I would like to pose now is, how do I tell these two possibilities apart? In other words, if I want to complete a thorough geometric characterization of the cross product, I want to be able to talk about the cross product in terms of perpendicularity and length and other geometric ideas, what's the missing piece that distinguishes these two remaining options? And the answer is a right-hand order argument. I'm just going to come back up to here. And someone's already helpfully pointed out that this determinant cannot be negative. Right? That means that this ordering, cross product VW, cannot be a left-hand ordering. And therefore, as long as nothing is zero or parallel or anything weird like that, this must be a right-hand ordering. Right? So specifically then, let me come back down here then. So this ordering, cross product VW, that is a right-hand ordering. Equivalently then, VW, V cross W. That is a right-hand ordering. And that will always allow you to distinguish between these two possible cases. Only one of these, exactly one of these, unless something is zero, will be such that, first vector, second vector, third vector in the direction of the thumb. Okay, so that, again, is what I had this different picture drawn here. Same picture, different point of view. But that right-hand ordering idea completes our geometric characterization. The cross product is the unique vector that's orthogonal to the two input vectors with a length equal to the area of the parallelogram, and that satisfies the right-hand rule. Namely, VW are the first two, and then the cross product in the direction of your thumb. So, complete geometric characterization. Now, side note, I have seen some textbooks that actually, when they talk about the cross product, they start with the definition of the cross product, this, and say the definition of the cross product is that it's the unique vector that's orthogonal, that has length equal to the area, and that satisfies the right-hand rule in terms of order. And then from that, they make arguments and they derive the formula. Right? And it's just as good. It's perfectly fine. It's arguably more natural to do it that way, because then you start off with a motivation for why you would be interested in the result, as opposed to what I did in this. I just wrote down a formula. Now the reason I just wrote down a formula and then derived, because it's easier to make these arguments. And there's something kind of nice about the sort of the reveal of the neat geometric properties that come about by starting with a seemingly arbitrary, uninteresting formula. So anyway, pros and cons, but yeah, beware. So a quick example, suppose I want to compute the cross product of E1 and E2. Well, now you can write down the formula, but you can also make a geometric argument and say, look, E1 and E2, I'm just going to do this hand waving, there's E1, there's E2. E1 and E2, they make a parallelogram, which is the unit square. I know what the area of the unit square is. The area of the unit square is 1. So E1, E2, their cross product has length 1. Furthermore, E1 and E2 are both perpendicular to the z-axis. So I know that this cross product that I'm trying to find, I know it's parallel to the z-axis, and it has length equal to 1. So that means, right off the bat, I know that the cross product is either E3 or negative E3. Those are the only two possibilities, right? Because of direction, perpendicularity, and magnitude because of that area of that parallelogram. So again, how do I distinguish between them? Well, E1, index finger, right hand. E2, middle finger, with my hand oriented in such a way that it bends the way it wants to point in E2's direction. And then look at my thumb. My thumb tells me that it's positive E3. So we can compute the cross product there without actually doing any arithmetic, simply by making a geometric argument. I think that's kind of a neat example. Let me pause for a moment for questions about any of what we talked about. Everybody happy? Okay. Moving on. Okay, next section, lines and planes. A lot of this is a review. You all have seen, for example, this equation before, y equals mx plus k. What is it, about 7th, 8th grade at this point? I feel like it might have been 8th grade for me. I don't remember. It was kind of a pre-algebra sort of bit. So long ago, right? The equation of a line in the xy plane, old news. And then here's another form for the equation of a line in the xy plane. Ax plus by equals c. So I was shown both of these equations when I was somewhere along in there, middle school. And I had a pretty strong preference myself. I liked this one, and I did not like that one, because the first one here, y equals mx plus k, the numbers that go into this equation had geometric meaning, geometric significance. I knew what m was. M was the slope. I know what slope is. I can see it. It's visual. K, the y-intercept. And again, I can look at a picture as geometrically satisfying in some way. But I felt like this was geometrically natural. And in this form, ax plus by equals c, I don't know, they never told me anything geometrically natural about that. I thought it was just sort of, I don't know, maybe organized in the sense that you have all the variables on the left and the constant on the right, but I didn't. So what? No geometric connection that was ever shown to me. Keep that in mind. I'd like to now motivate the equation of a line from a different point of view using dot products. And what I'm going to do is consider the question. Suppose I am given a point on the line in question. Suppose I am given what I'm going to call the normal vector for the line. And normal in this context means that it's perpendicular to the line in question. That's just a, sort of an alternate use of the word normal. So given a normal vector and given a point on the line, I claim that uniquely characterizes the line. There is only one line that can be perpendicular to that vector, and that goes through that point, right? So, all right, fine. So if I wanted to describe, come up with a condition, some rule that I could write down that would help me decide if this point is or is not on the line, how would I go about doing that? Keep in mind, let's pretend we don't know what the equation of a line is so far. But here's a point. I want a decision. Is that point on the line or not on the line? And the way I'm going to argue is that this difference vector, if x is on the line, that difference vector would have to be parallel to the line, and therefore perpendicular to the normal vector. So write that down here. X is on the line if and only if the difference is parallel to the line, and therefore perpendicular to the normal vector. So what's nice about this is that this form here, perpendicular to the normal vector, is something I can convert into algebra. Specifically, perpendicular means dot product equals 0. Right, does everybody remember that? Let me zoom in and make that a little bit more visible. This is one of our big results about dot products. Two vectors are perpendicular if and only if the dot product is equal to 0. We call this orthogonality. Right? Okay. Yeah. All right. So then let's take this equation here and distribute the dot product, move the one thing to the other side of the equation, and it comes down to this, which is fine. And then, well, n is a given vector. It's going to have some coordinates. Let's just say its coordinates are a comma b, and n and x naught are both given, so this is just some number. I can compute that number. N is given, x naught is given. Multiply and add, compute this dot product, it's some number. Let's call it c. And then look what this equation turns into. The normal vector with its coordinates a and b, this dot product, dot product being c, and this equation that we just derived becomes the equation that I never liked when I was in middle school. Right? Everybody happy? Okay. So what's the punchline of this? The punchline is that these numbers a and b that I had so much contempt for when I was in middle school are geometrically natural. They just never told me. Okay? And it's reasonable that they didn't tell me, but nevertheless, with these numbers a and b, keep in mind what they are. They are the coordinates of the normal vector. So these two numbers tell you a vector perpendicular to the line. Botched my color coding here, but so they are geometrically natural. And the reason they didn't tell me is because being able to make that justification involves using dot products, and they just hadn't talked about dot products in middle school, of course. Okay. So anyway, I think it's a nice derivation. I like to point out that this equation is actually more useful than it gets presented as being in the last time that you saw it. And secondly, this argument that we've just made is a fantastic segue into something you might probably have not seen before, which is instead of talking about lines in R2, let's crank it up a dimension and talk about planes in R3. So two-dimensional planes in a three-dimensional space. So our picture looks like this. So now, assume we don't know anything about the equation of planes or how to write down equations that describe planes in any particular way. I observe that if you give me a point on the plane and a normal vector, that completely characterizes the plane. There's only one plane that can be perpendicular to that normal vector and go through that point. Question: how would I go about deciding about another point, x? How would I decide if that point is or is not on the plane? Well, I would decide by whether or not the difference vector here is parallel to the plane, and therefore whether that difference vector is perpendicular to the normal vector. I hope that sounds familiar. We're basically going over the same argument that we made for lines in R2. Same thing, one dimension up. So here's the algebra. It's on the plane if the difference is parallel to the plane, aka the difference is perpendicular to the normal vector, and then here it picks up in the same way. Perpendicular means the dot product is equal to 0. You can take this dot product and distribute and move around, etc., and you end up with what looks like, in fact, exactly the same equation that we had for lines in R2. It really does look the same. N dot x equals n dot x naught. The only difference between this equation for a plane in R3 and the previous equation, n dot x equals n dot x naught, for a line in R2 is that these are three-dimensional vectors. It just doesn't show up in how we write it down. Other than that, yeah, really same equation. So being as these are three-dimensional vectors, that normal vector is going to have coordinates. Let's call them a, b, and c. Again, n and x naught are given, so that's just some number. Let's call it d. And here then is the equation plane in R3. Very analogous derivation. Nice application of dot products. Everybody on board? Yeah.
So would this be possible in like R17?
Absolutely. Yep. If you want to talk about the equation for a 16-dimensional plane-like thing, right, that lives inside of R17, that's right. It will be described by a point in that 16-dimensional thing and a normal vector, and namely a vector perpendicular to that 16-dimensional thing, and then the exact same argument, totally. Yep. Yep. Anybody else? Great question. All right. So my personal preference, by the way, is to think of these equations in that term. In other words, to think of it as a statement about dot products and points and vectors. Because this is something that's going to segue, that's going to connect more conveniently to the way we're going to be dealing with these kinds of questions. Is we're going to be given points, and I want to find the plane that's parallel to this line and goes through that point and perpendicular to this other thing. And so we're going to be given geometric information about the object we're looking for, and this explicitly tells you what to do with what particular geometric things, namely what's perpendicular to the plane and what's in the plane. Right? So this is arguably more geometrically natural. It's just that it involves notation that involves, you know, operations that are kind of new and sophisticated. This is elementary school arithmetic. It's got that appeal, right? But ultimately, this is the more useful one. So I encourage you to think of the equation of a plane and the equation of a line in R2 this way. Okay, so here's a quick example. There's a unique plane that passes through that point, and that's perpendicular to that vector, and this is a plug and chug. That is my normal vector, and this, whoops, sorry, that is my x naught, plug and chug, and here's your equation. Equation is that. Anybody see what happened there? Just literally plugging into that equation.
With those sorts of problems, would you want us to show like all of the?
Yeah, I mean, you should always show something on any exam question, any homework question. There should be something somewhere to show, right? And so in this case, yeah, even something as little as what I've done here, I could have shown even a little bit more. I could have said n equals that, x naught equals that, n dot x naught equals, and then write this down, and just just a little bit of exactly. Any question I ask you will involve thought, and I just want to see evidence of the thought. Yeah, right. Okay. Here's a different example. This is a little bit trickier. This is representative of a category of questions that y'all will see sometimes here and there, which is there's a sort of a puzzle component. Namely, I'm going to give you certain geometric information, just not the geometric information that you in fact exactly need, and the puzzle is to take the geometric information you're given and figure out what you can do with it to deduce the geometric information you need. And in this case, I'm giving you, I'm looking for the equation of a plane, and what I'm giving you is 3 points on the plane. These 3 points here. And so, well, what we need is a point on the plane and a vector perpendicular to the plane. I don't have that. I have a point on the plane. Take your pick. I need a vector perpendicular to the plane, not given. So thus begins the puzzle. And the argument to make is here's a sort of a picture. Do I have a second? No, okay, it's fine. Here's a picture. These are the 3 points I'm given. And I just observe that with those 3 points, I could look at, for example, b minus a. Now I have a vector parallel to the plane. If we look at c minus a, now I have another vector parallel to the plane. So I have now 2 vectors parallel to the plane. Again, not what I need. But I have a handy dandy tool called the cross product that if I have two vectors parallel to a plane, their cross product is going to give me a vector perpendicular to the plane, and that's what I need. So this is the little Rubik's Cube move that happens to solve this particular little puzzle. If you have 3 points, pairwise differences, vectors parallel to the plane, cross product, there's your vector perpendicular. So this kind of game comes up in lots of different questions. There's several of them in the exercises that y'all will be working on for this section. And just think about what you're given, think about what you want, and start thinking about what you can do to get from here to there. Okay, so this, once you have that normal vector, the cross product of those two difference vectors, that normal vector lets you deduce the equation of the plane. Side note: which of these three points should you pick as the x-naught? Doesn't matter, right? In some sense, what the equation of the plane says here, if you look at the equation of the plane, it says that any vector in the plane, doesn't matter which one, any vector in the plane, the dot product with the normal vector will always be the same. Right, so pick whichever one looks most convenient, most arithmetically convenient. In this case, gosh, I mean, I could have picked any. Which one did I pick? Where's? Yeah. Oh. Huh. I didn't indicate which one, but I like this one best. It's got smaller numbers in it. Right? My inner laziness says, hey, let's use that one, and it's fine. It doesn't make any difference. Okay. Okay, so we've talked about lines in R2, planes in R3. Now we're going to do something dimensionally a little bit unanalogous, lines in R3. So previously, line in R2, plane in R3, the things we were describing were one dimension less than the world that we were living in. And that's, in some sense, why there was that analogy. Is that very similar, really. Here, we have something of one dimension in a three-dimensional world. This is different. Okay. So the way we're going to do this is, given a line that I want to describe, I'm going to need a point on the line. It wouldn't do to give me a vector perpendicular to the line, because if I say vector perpendicular to the line, well, there are actually lots of lines through that point that are perpendicular to that purple vector. Right? So that doesn't, it just doesn't characterize the line. It doesn't. So instead, what we're going to do is say, give me, in addition to a point on the line, give me a vector parallel to the line. So in this particular little situation, it's a parallel vector that's just that more naturally and conveniently describes the way this line is kind of oriented, if you will. Does that make sense? Everybody see why we sort of can't go with a perpendicular vector? It's just not enough information. I guess we could go with two perpendicular vectors, but again, that's more effort than this. Okay. All right, so given that, how do I decide then on this point? How do I decide if a point X is or is not on that line? I'm going to make a very similar kind of argument, and the idea is that this point is on the line if and only if that difference vector is parallel to the line and therefore parallel to the given direction vector. So we write that down. Let's see, where did I put? Oh, it's down here. Yeah. Oh, do I have? Okay. So points on the line if the difference is parallel to the line, namely also parallel to the given direction vector. Fine. So now how do I characterize this? Now here's where we previously we were looking at something that was perpendicular, and the way we express perpendicularity in algebra is by a dot product. How do we express parallel? Well, there's actually a kind of an easier way to do it. If these two vectors are parallel, then one is a scalar multiple of the other. Or one of them 0, perhaps, but no problem. So, said differently, if you just solve for x in that equation, what you get is this, that every point on the line, every point x that's on the line that I'm interested in has to be of this form. It has to be x naught plus some scalar multiple of the direction vector v. So I can write the line like this. The line is the collection of all vectors of this form. Now, the very first thing I want to point out about our little result here, our description of the line, is it's not an equation. Right? When we were looking at the equation of a plane, we had an equation. This equation here, that equation, that is a test. You give me a point, x, y, z, I can plug in and I get either a yay or a nay. And the equation just decides for me. These two numbers either are or are not equal. Right? And I don't have that. What I have here now is it's not a decider exactly. If you give me a point, well, I mean, I could, the way I would have to decide is that I have to write the point here and then see if I can find some t that will make that work, and we'll talk about how that might work out. But the point is, it's not an automatic thing. I can't just plug it in and get an immediate thumb up or thumb down. That's just not what this is. So it's inferior in that way. Equations are tests, and they just tell you the answer. This either is or isn't in the line or plane. Now, what we have here, though, is better in a different way. I have here a little factory that will create points on the line. I can pull out of thin air any value of t, throw it into here, and bam, there's a point on the line. This is a little point generator, and it generates nothing but points on the line. That's nice, and equations don't do that. The equation is a test, but it's not a factory. Right? You have to come to me with the point to test if you want to use an equation. This creates points. So it's kind of a difference, a different sort of algebraic object, and a different way of describing a geometric object, generating instead of testing. Okay, so anyway, this is called a parameterization of the line. The reason we call it a parameterization is because every point on the line is being described in terms of what they call a parameter. The t here is called the parameter for this line. So for every point on the line, there is a corresponding value of t. Okay, we're going to say a lot more about parameterizations in a couple sections in the future. Okay, so here's an example. Suppose I want to describe the line in R3, so it's going to be a parameterization that passes through this point and that point. Well, keep in mind what you need if you want to talk about a parameterization. Here's what you need for a parameterization. You need a point. No problem, I have two. And I need a vector parallel to the line. I don't have one. I have 2 points on the line, but what I need is a vector parallel to the line. And so that's when I go back to this equation. Here are the 2 points that I'm given. I need to find a vector parallel to the line where, given these 2 points that I have, where might I find a vector parallel to this line? And, well, let's, take their difference. That difference is clearly parallel to the line, and I can use that. That make sense? Okay. So that's what I've got here. You'll notice that we use the difference b minus a as our direction vector. Either of these 2 points would have been fine to use as the starting point. I use that one, no particular reason, doesn't matter. And there's your parameterization. Now, I will say that while doesn't really matter whether you use this point or that point. You get different parameterizations depending on which one you use. Using as I have this point A as my starting point, I get a parameterization, and this does indeed generate the whole line. But if I had used this other point, I would have gotten a different parameterization. It would still parameterize and create and generate the whole line, just sort of from a different starting point. So in other words, starting here, we generate in such a way that this is where t is equal to 0, and that's where t is equal to 1, and then you can probably sort of guess this is where t would equal to 2. If I had used B instead of A, then this would have been where t would be equal to 0. So it's a different parameterization, but it still traces out the whole line. Okay. So parameterizations are not unique. There's different ways to parameterize the same thing. Okay. Here's a fun little example. Got a line and a plane. Got a line from the previous example, and I want to know what point on that line is also on the plane with that equation. So said differently, I want to find where does this line intersect this plane. So I've got two geometric objects. There's a plane, there's a line, and that line punches through that plane at a particular point. So let's find it. So this is a great example in a certain way. What I like about this example is I have two different kinds of information. I have, on the one hand, a parameterization of the one object, and I have an equation for the other object. So here's our parameterization of our line, and then I have an equation for the plane. This is a point generator. This is a point tester. And what I want is a point that works for both. Said differently, I'm going to generate points and then test them. Right? I generate points that I know are on the line and then test to see if they're also on the plane. So basically, I'm going to take this formula for generating points on the line. This is going to create for me my x, y, and z, and I'm going to then plug into that equation and solve for t. And that's here. Actually, let me do a little bit of one quick thing here. This parameterization that I wrote down. It's a little bit more useful in this case to write it vertically. 431 plus t 303, because in this way you can see right away there's your x, there's your y, and there's your z. Right? So x is 4 plus 3t, y is 3 plus 0t, and z is 1 plus 3t. Right? So that's one of the reasons I like the vertical notation better than the horizontal. Anyway, those are the x's, y's, and z's that you then plug into here. So x, y, orange, z. Notice that in the equation, the coefficients, I guess I'll do this in red, the equation coefficients are 1, 1, and 2. That's the 1, 1, and 2 there. So all I have done is I've taken literally the points on the line, the points generated by the parameterization, plugged them into the equation, and then it's just a question of solving for t. And t ends up being, in this case, -1, and that -1 generates that particular point on the line, and that's the point on the line that's also on the plane. Everybody on board? Happy? Okay. Fun little example. So one last thing I want to show y'all. Here's our parameterization again. sort of a different way of writing down the parameterization. I'm writing it as three separate equations. So as you can see, this comes from x, y, z vector equals x naught, y naught, z naught vector plus t times abc vector. Parameterization. Suppose I want to create a test. This is a generator as it is, right? This generates point. You give me a t, plug it in, bam, there's your x, y, z. It's making points. Right? I want to turn this into a kind of an equation kind of deal where I want to be able to come with a point and test and see does it work. So there's a slick move for this, and that is to realize that if there is a way for this to work, then it has to work for a particular value of t. Namely, you have to be able to generate the given x with a particular value of t, and then for that same value of t, you have to generate your given y, and for that same value of t, you have to generate your particular z. So, said differently, if you solve for t in all three of these equations, all three of those t's have to equal to the same things. In other words, you have to be able to generate the point in question with one single value of t. Well, notice if t has to equal to three different things, those three different things, in fact, are not different. They're all equal to each other. Three things all equal to t, those three things are equal to each other. And conveniently, what you get then is something kind of like an equation. What it really is two equations, arguably three equations, depending on how you look at it. And this is your test. So if you have somebody comes to you with a particular point and says, I would like, here's my XYZ, I would like to know if this XYZ is on this line that you have parameterized. What you need to do is pull this trick, namely solve for t, set all three of the results equal to each other, and there's your test. So you take the x, the y, and the z that are given and compute all three of these expressions, and they better all equal to each other. If they're all equal to each other, then that thing that they are all equal to is the value of t that will generate the point you were given. If they're not all equal to each other, then what t could you possibly use? You just can't, there is no value of t that's going to generate that point. Does that make sense? Everybody happy? Okay, so this is called the symmetric equations for a line in R3. Given a parameterization, you can write down the symmetric equations. Given the symmetric equations, you can do the argument in reverse and write down the parameterization. Keep in mind the path in between these two is solve for t. You know, in some sense, the path in between these is the realization that these three things are supposed to equal to t. Okay. All right. So now there's one last thing I'm going to show you concerning the symmetric equations, namely. It is kind of three equations. That's an equation. That's an equation. But then also, that's an equation. And the question I'd like to consider is separately, individually, what are these individual equations representing? So I'm going to look at this one, if I remember correctly. Look at the picture here. Which one did I? Yeah. Okay. So what does that equation look like? What does this represent? Well, I'm going to make a couple of observations. First thing I'll observe, this is the equation of a plane. This is an equation, I mean, we're talking about in R3, we have points in R3, and this is an equation that if you were to kind of multiply and rearrange terms a little bit, you'd have something times x plus something times y plus, well, there aren't any z's, but plus 0 times z equals a constant. So this is the equation of a plane. It's just an equation of a plane where Incidentally, one of those coefficients happens to be 0. So what? Still a plane. So that's a plane, fine. The other thing I can point out about this is that points that satisfy the symmetric equations also satisfy this one equation. It's sort of a silly observation. If an x, y, and a z have the property that all three of these things are equal, then it follows from that that these two things are equal, right? An innocent observation. Geometrically, what that says is that the line, all the points on the line, happen to also be on that plane. So this is not just any old plane. This is a plane that contains the line. And the last observation, or this little trio of observations, is that this plane, claim that this plane is vertical. Think about that a couple of different ways. One way to think about it is, what's the normal vector? Well, we made the observation that I could rewrite this as, something times x plus something times y plus 0 times z equals, I don't really care. And the punchline is that the normal vector is question mark, comma, 0. That means the normal vector is horizontal. I don't know exactly what way it points, but it's a horizontal normal vector, and that means that the plane is vertical. So this is a vertical plane that contains the line. And in fact, there is only one such plane. Containing this line right here, there is exactly one vertical plane containing it. This is what I would like to call the vertical shadow plane. In other words, if this green line were actually suspended up here in space and if the sun were straight overhead, this is the plane that describes the shadow of that line. That's kind of geometrically natural. Said differently, this plane is the unique plane that you get when you take this green line and sort of drag it parallel to the z-axis. So that is what this is here. That line, that plane there is this purple plane. And by a very similar argument, I'm going to leave as an exercise for y'all. This is a plane that contains the line and that is parallel to the x-axis. So it's kind of the shadow plane, if you will, if the sun were at sort of at sunset, when the sun's in the direction of the x-axis. Yeah. And then the other equation, this, let's see here, I'll use yellow. That equation, that's a plane containing the line parallel to the y-axis. So the symmetric equations are, in fact, and it's kind of a cool fact, the symmetric equations for a line are describing the three sort of axis shadow planes that all come together to describe that line. It's geometrically interesting. Everybody happy with that? So it'd be a great exercise. See if you can sort of go through, maybe even write down the arguments that justify the blue plane and the yellow plane. It's going to be very analogous to what we did with the purple. Yeah. Questions? All right. We're going to go really quickly through the next couple of sections. There are only a few things to say, really. So before I get into coordinate systems, curiosity, how many people have seen polar coordinates before? Quite a few. Okay. If you haven't, no big deal. First, let me just describe what a coordinate system is. Coordinate system is a means of describing where a point is by giving certain numbers. The rectangular coordinate system is described by these numbers x, y, and z, and the way I'm describing, what do those x, y, and z mean in the context of Math 212 is, well, you make a rectangular box, like so, and then where the box intersects the x, y, and z axes are the x, y, and z coordinates. So that's rectangular coordinate system. So that, however, is not the only way to describe points. There are different ways to do it. So here's a picture in R2 of something called the polar coordinate system. Given a point, sure, I could describe its location by its x and y coordinates, right? Absolutely. But I could also describe it by first telling you what this angle is. You know, how far would you need to rotate counterclockwise from the positive part of the x-axis? How much would you have to do this, right? Describe the direction. And then how far would you go in that direction? If I give you a theta and an r, that would also describe that point. So that's called polar coordinates. And there's some equations that you can write down that relate x and y and r and theta. And we'll write those down in a few minutes. Before I do that, I want to observe some awkwardnesses, though, about the polar coordinate system. In other words, I can describe this point P by that theta and that r, sure, but I could also, technically, let that be my angle theta. It would be 2 pi plus whatever the original angle was. That would still point me in the same direction. So theta is not unique. Right? It's not a well-defined thing. The same point you can describe with different polar coordinates. That doesn't happen in rectangular coordinates. So if you have a point, it has a unique set of rectangular coordinates. Polar coordinates are not unique. Here's a weirder point of view on that same thing. I could do that, thus describing that I should go in that direction. And in that direction, I should go a negative distance. Right? That would still get me to that point. So, a little bit awkward. You have to realize that there's different ways to describe the same point in polar coordinates. So that's awkward. Also awkward, where's the r-axis? There isn't really an r-axis on this picture, right? There's not really a theta axis particularly on this picture. So that's awkward. One of the nice things about the x-y coordinate system is they have these axes, which are reference points, if only visual reference points, that help us kind of keep track of where we are and what we're doing. Polar coordinates, weirder. Okay. Nevertheless, even though most of the time rectangular coordinates are better, or nicer, they have nicer properties, there are some situations where polar coordinates are extremely nice, very useful here and there. One big advantage of polar coordinates, I'm just going to throw this out there very quickly, is that they're much better at describing circles. Right? The way you describe a circle in rectangular coordinates, you have to bring quadratics into it, right? X squared, y squared, etc. In polar coordinates, r equals a constant. Very easy to describe circles in polar coordinates. Now, why does that matter? Well, because the world is full of circles, unavoidably. Right? And so it's a big deal. Polar coordinates, very useful in some situations. Now that we have a second coordinate system in R2, let me point out that there is a potential for confusion. So, for example, if I write, 1 comma pi. If I just write only 1 comma pi, what do I mean by 1 comma pi? Well, it's tempting to say, oh, well, that 1 looks like an r, and that pi, well, that looks kind of like, that pi is a pretty common, angle. So it's probably that's an r and a theta. The problem is, even though that may be the case, there is a point where x is 1 and y is pi. That's an actual point. So using ordered pairs, when you're describing points that are either, well, it might be in the polar coordinate system, might be in the rectangular, there's an ambiguity when you write that down. Now, I have a means of addressing that, and it's not particularly standard, but I like to put down a little subscript like this. So if I say x comma y and a little subscript of r, that's just me saying, hey, by the way, these are the rectangular coordinates of the point that I'm talking about. Okay. And then that same point, maybe I call it P, that same point, maybe it has polar coordinates, r and theta. So I could write down r comma theta, but I don't want there to be the confusion that maybe you think that's the x and that's the y, so I put a little p subscript to indicate that this is polar coordinates. Therefore, that's the r, that's the theta. So this is just a little thing that I made up to do this. So now I'm going to use that notation to describe some of the relationships between the rectangular coordinates and the polar coordinates of a point. And specifically, I'm going to relate them by writing down the relationship directly. These are rectangular coordinates here. So that's x, and that's y. All right, now notice both of these are in rectangular coordinates because it says r subscript to both of them. And what this says is that the x coordinate can be computed as r cosine theta, and the y coordinate can be computed as r sine theta. And what do I mean by r and theta? Well, r and theta are the polar coordinates of that same point. So anyway, I like to use that in situations when there's some uncertainty as to exactly what you're referring to. It's nice to have that little language. Okay. All right. So next coordinate system, cylindrical coordinates. Cylindrical coordinates is a lot like polar coordinates. There's the polar r, there's the polar theta, and it's just that if you're talking about points in R3, you also need to talk about a height, z. So here's a picture of cylindrical coordinates. A point is described by a theta, an r, and then a height z. Very similar. It's in some sense kind of like a polar coordinates in R3. Okay, fair enough. Okay. There's not that much more to say about it. The usual formulas. So x is still r cosine theta, y is still r sine theta. Okay, spherical coordinates. Now this really is different. Some people refer to this as polar coordinates for R3. I am highly opposed to that terminology. This is really very much different than polar coordinates. So specifically, the distance that gets referred to is not that distance there. This is your r. This is your distance from the x-axis, from the z-axis. The distance in spherical coordinates is that distance. It's the distance specifically to the origin. It's not the same. Right? So this is your r. That is not r. We use the lowercase Greek letter rho to represent that distance. And side note, it does look kind of like a p. It's not a p. So please be careful with that. Don't write it as a p. In fact, you might want to take a few minutes and sort of practice making these little symbols. They're kind of little swirly things like that. So it's not like that. Everybody see the difference? Okay. All right. Right. So then, but it does use the same theta. That's the same polar coordinate theta. And then there's another new coordinate that it uses, and that is this angle phi. That's the lowercase Greek letter phi. It actually looks kind of like a theta turned sideways. So phi is an angle also measured off of an axis. It's measured from the z-axis to the line going directly toward the point. Now notice theta doesn't go toward the point. Theta is measured from the x-axis, but it goes over to the shadow line. Right. So phi and theta are definitely a little bit different there. Okay. It remains though that if you give me a rho, a phi, and a theta, well, given the theta, given the phi, that defines the direction given a rho. That tells you how far to go in that direction, and that gives you that point. Okay. Again, there are ambiguities. There are fun little games that I'm going to have you all play on the exercises where you will, given a point, note that there are actually kind of 4 different ways to describe that point in spherical coordinates. And when I say different, obviously you can add 2 pi to the angles. Nothing. That's all sort of obviously going to always give you the same point. But so there's 4 otherwise qualitatively different ways to describe that point. And for example, you could, instead of using that angle theta, you could use that angle theta describing that direction. Let me do a better job with that. Describing that direction, sort of going the wrong way, if you will. And then the phi that you would use, so the angle off of the z-axis there, in that direction you would go a negative amount. So you, in some sense, you can add pi to your theta and make phi negative, and it still points you in the same direction. Or you could have phi be that angle. I'll let you all think about what that would be. That would get you going in exactly the wrong direction, and then have rho, in that direction be negative. Another way to get to that same point, and there's a 4th one. I'll let you all figure that one out for yourselves. I want you to write down all the 4. That's one of the homework exercises, to write down all 4 of the different ways to describe, and then I give you an actual particular point in all 3. So it's a good muscle building, geometric visualization, muscle building exercise. Okay. One last thing, and then we'll call it a day. And that's let's talk about how equations work. So, for example, suppose I want to have a polar coordinates equation for a circle. Well, obviously, sometimes this works out nicely if it's a circle centered at the origin. R equals A, super convenient. Right? But what if it's not centered at the origin? What if we have a circle, radius A, but centered at a different point? And how can I write down the equation of that circle? And let's see here. I don't have a picture of this, I guess. I'll draw a quick picture. So the picture here is it's centered here at A comma 0, and it has radius A, which means that it goes through the origin, and it kind of sideswipes the y-axis there. So how would I find the equation for that circle? Well, r is simply not a constant here. R, if you notice, being the distance from the origin, r takes on very different values depending on the theta. Keep in mind, r is always measured from the r is always measured from the origin, not from the center of the object that you happen to be dealing with at the moment. It's always from the origin. Okay. So what do you do about this? How can you describe what r is as a function of theta? There we go. Close enough. So the way we do this is if we write down the rectangular equation. Now this is old news, algebra 2. Right? You can write down the algebra 2 rectangular equation for that circle. X minus a squared plus y squared equals a squared. This gives you the center and gives you the radius. Okay, old fact. And then just multiply it out and make the appropriate substitutions. Just don't forget that x is, I'll do it like this. Multiply it out, collect a few terms, and then x is r cosine theta. That x, r cosine theta. This y, r sine theta. You just plug in what x and y are in the coordinate system that our new coordinate system is the polar coordinate system, and note we get an equation in polar coordinates, at which point you just can do a little simplifying. Now here we get lucky, and there's a sine squared plus cosine squared thing going on there. That's always 1. That's nice. And thus you get this simple little equation for r as a function of theta. Now, having seen how that worked out, let me also point out that you could cleverly have noticed that the x squared and the y squared there, that eventually turned into an r squared. You could have just done that immediately and said x squared plus y squared, and just written it as r squared. That's a slick move. That's a good thing to be on the lookout for, that you don't have to do x and y individually as r cosine, r sine. If you see x squared plus y squared, that is r squared. You can plug that right in. Be careful with square roots. It's tempting to say that r is the square root of x squared plus y squared. Not necessarily. R is allowed to be negative. Right? Square roots are, that symbol square root means positive square root. So you've got to be a little bit careful with that one. Okay, so that finishes that section. We are out of time. We'll call it a day. And yeah, see y'all later.